Good morning. Today I want to show you something that very likely strays quite deeply into the do not try this at home territory, and this is something that came out with some discussions on the QRP Lab forum, QRP Labs forum, and the discussion was about how useful it might be to have an additional serial terminal on the QDX so that the operation of the QDX could be monitored live or things adjusted in the QDX while the actual other serial port was connected to the CAT to WSJTX via the CAT control. So then the discussion moved on to VT. Then the discussion somehow moved on to VT220 terminals, which was many decades ago a terminal used for accessing mainframe computers, and it consisted of a small CRT monitor and a keyboard, and these terminals were available in amber, green or white colour phosphor, and it has a nostalgic value for me because I used that in my first job back in 1994, which was on a VAX BMS mainframe system. So of course I looked around and nostalgia a bit, and I looked on eBay, and these things are there but very, very expensive, and to get it here into my location here in Turkey would be even more difficult, and of course there are none here that I could find. And so what did I do? I did what any good hacker should do, which is build your own. So here is my VGA monitor acting as a terminal, and it's using the microcontroller on a QDX board to generate the VGA video signals directly and interface to this PS2 keyboard directly as well by bit banging the data lines to the PS2 keyboard. So this requires quite some fine wires to be connected to microcontroller pins on the STM32 micro on the QDX, which is why I say really you probably shouldn't try this at home. If you do decide to try at home, please do not get in touch with me if you break something, and I do not want to hear from you. I don't want to hear from you until you just order a replacement QDX, because this is really something you should do only at your own risk. You might be wondering, does this QDX still function as a QDX while it's generating this VGA output and the PS2 keyboard input? And the answer is yes, it does. The VGA output and keyboard input have been added to the QDX. It's not just using the QDX as a board to provide the functionality. It's functionality which is actually added and built into the QDX, and the QDX still operates perfectly as a QDX. So here on the left, this is a QLG2 GPS receiver, which I'm here just using as a USB to serial converter for reasons which will become apparent. Over on the right I've got my dummy load and the QDX here in the middle. I'm running on a very low power supply voltage, not that I'm nervous or anything. Here I've connected a VGA monitor and a PS2 keyboard, obviously using completely standard connectors. In fact, I have sawn off a piece of another PCB and put on two 4-pin headers, and using those to make the connections. What you see here is a VGA monitor, which I used to use in 2006 for a PC I had in those days. And on the PS2 keyboard, if I press enter, it will initiate the VGA subsystem with this splash screen, which is modelled on an original VT220. I have renamed this QVT220. Of course you know what the Q stands for. Now if I press enter again, I get the usual terminal entry into QDX, and everything works as normal as it would on the terminal emulator on a PC connected to a QDX. I tried to emulate an amber coloured monochrome VT220, and this is achieved by using the menus in the monitor itself, and there's actually a menu here that allows you to set the levels of the colours individually. So I just changed the green level to 70%. So the video output from the microcontroller pin is connected to the red and the green input signals, and to get the amber colour you use 100% red and about 70-75% green, and it produces this nice amber colour. In my new firmware version, QDX now has 3 serial ports as well as the onboard VGA and PS2 terminal outputs, and all of this can be enabled or disabled in the configuration here at the bottom of the configuration. So to go through this, the VGA PS2 terminal is enabled and disabled here at this setting, and you would do this on the USB terminal emulator to start with. Each of the 3 serial ports is enabled by setting its baud rate here in one of these 3 settings at the bottom, and if you set it to 0, that serial port is disabled, and that will be the default. So here I've set terminal 3 to 38.4K baud, and terminal 3 is actually connected to the same GPIO pins as the PTT positive and negative in the QDX version 3 PCB and version 3A PCB, which is connected to the 3.5mm output jack. So there's actually 2 transistors driving those PTT signals on the 3.5mm stereo output jack, but if you want to use that as a serial terminal instead of a PTT, you actually need to remove those 2 transistors and just bypass them so that the GPIO pins are connected to the 3.5mm stereo jack and can function as a serial port. The function of the PTT port is now determined by this setting, and you can see here I have it set to serial 3. You would by default have it set as a PTT port, but you can also set it as an auxiliary output port. So then those 2 levels will be driven according to the specification in the band configuration here at the bottom on receive and on transmit. So you would use that if you want to use 2 relay control outputs, perhaps to switch between different antennas, for example, and that was a request from one of our users to do that. So if you didn't want to use PTT for an actual amplifier control, you wanted it always to be on as an auxiliary output control for something, you can set that to AUX, and you can also set it to serial 3 as I've done here. Now, so this QDX now has 5 serial ports, 3 using USARTs on the microcontroller, 1 being the traditional USB virtual COM serial port, and the 5th one being the combination of the connected VGA and PS2 keyboard. So what I'm showing here now is on the main PC monitor, and on the left hand side I've got the ordinary USB terminal emulator, and on the right hand side I've got serial port 3 connected via the QLG2 GPS receiver board, which is being used as a USB to serial converter. Of course you could use any USB to serial converter here. And what I want to show you is actually all of these 5 serial ports are orthogonal and independent of each other. So you have a separate terminal session on each of the 5 serial ports if you've however many you've connected. And usually the USB serial port would be used as the CAT control from WSJTX, etc. But you could do it any number of different ways. So here on the left hand side you will see that when I go into one of the screens, such as the configuration screen, that setting on the right hand side here goes red, which indicates that the screen cannot be opened on the terminal on the right hand side. So basically there is this concept of now here I am controlling the terminal on the right hand side. You see it's slightly slower because it's 38.4K baud, whereas USB terminal emulation is much faster than that. And so on either side I can go into any of the screens, but it will then disable that on the other one. So the screens are not multi-user, but the menu system is. Some of the screens, for example the log file here, they are multi-user. You can do them on both sides with no problem. now you can see I've opened WSJTX. I have it on 20 meter FT8 mode, receiving FT8 stations, and I have the USB to serial converter, the QDX, on serial port 3 on the right hand side. Now you can see here that these audio filter sweep, RF filter sweep and transmitter test have gone red. The reason for that is because now the CAT control is in charge of the radio on QDX, and you can no longer then use the terminal to do audio sweeps, RF sweeps or transmitter tests, because that resource, the radio essentially, is now reserved by the WSJTX via CAT. But if I go into the input analysis screen and I do tune here on the WSJTX, you can see that signal come up. If I was to enable a transmission, then you would see the analysis of that transmission as it plays out in real time. So the frequency is up here at the top right hand corner, and all of these are the tones changing as the transmission proceeds. You could also do things like change the gain if you wanted to adjust the gain in real time to get it to a level that you were happy with. You would be able to do that here. Another CQ has started, so I'll just click Halt to stop that. So, as I said, you'd be able to go in here and change the audio gain or any of the other things that you might want to do. Another very interesting application is a new one which I've added, which is CAT Monitor. And what this does is show you all the incoming CAT communication in real time. So if I close WSJTX, you'll see it just emits these two CAT commands on closing it. But if I now restart it, you see a whole bunch of CAT commands come up as WSJTX starts. If I click on Tune to enable transmission, you'll see that happen there. If I was to change, for example, to the 40 meter band, you can see the command here to change the 40 meter band. So this is a real-time log of all the CAT commands coming out of WSJTX. So that's quite an interesting new screen which I've added in this firmware. Now I'm going to say something about how this is done. Now, on a old CRT monitor, an old-fashioned television, the screen was like this, and the electron beam traversed from left to right and then very quickly flipped back and traversed from left to right again and went back left and right again, and it did that until it reached the bottom of the screen, and then the beam flipped back up to the top of the screen and the whole thing was repeated, and it did that 50 times per second. Now, all video standards since the old days, many decades ago, still have the same format for how they are being transmitted. So you have a scan line, and each scan line takes a certain amount of time and contains a synchronization pulse as well as the actual period of video here which is displayed. So as the beam sweeps across the tube, you want to change the intensity of the video as it sweeps across to draw one line of the picture. And then you move on to the next line and the next line and the next line, and at the end you generate a vertical synchronization pulse so that the monitor knows that it has to sweep back the beam to the top of the picture. These synchronization pulses are actually inverted like that on a VGA standard. So how this is generated on the STM32 microcontroller, we use 3 output pins, one for the video, one for the horizontal sync pulse, and one for the vertical sync pulse. Now the horizontal sync pulse is generated by one of the timers and using a PWM output, so that's fairly easy to generate. You can also generate interrupts, for example here at the completion of the horizontal sync pulse. The video is generated using the SPI peripheral, which is basically like an 8-bit parallel to serial converter. So it takes in an 8-bit byte here and it converts that into a series of bits sent serially. So each of the pixels on the display is one of these 8 bits, and this one might be coloured in, this one might be coloured in. So we would send an appropriate 8-bit byte that when it's converted to serial looks like that. And then we do that 100 times across the whole display, and we have 800 pixels across and 600 pixels vertically. That is repeated 56 times per second, and that basically leads to a pixel rate of 36 megahertz, which is half the STM32 clock rate of 72 megahertz. So the maximum frequency that the SPI peripheral can be clocked at is half the CPU clock rate. So 36 megahertz in this case, which is perfect for the SVGA standard, which is 800 by 600 at 56 hertz. So we have the horizontal synchronization pulse, which occurs once per scan line, and then every 625 scan lines we have a vertical synchronization pulse which covers 2 scan lines. Now some people use 2 timers. It's possible in the STM32 to use 2 timers and to define events in the first timer that trigger the second timer. And so by doing that, it's possible to chain together these 2 timers and have one generate the horizontal synchronization and the other generate the vertical synchronization. However, the timing of the vertical sync is not very critical, and so I just did it with some code in the interrupt which occurs at the end of the 8 sync. So it literally just sets an I/O pin, and it takes 2 lines of code to do that. It's probably less code than it would take to set up the timer in this arrangement, and it's not critical at all, so it was just the easy way for me to do that. Now this STM32F401 that's used in the QDX has 64 kilobytes of memory. An 800 by 600 monochrome display would require 60,000 bytes of storage for a frame buffer, so it would use almost all the memory. Now the QDX is also doing SDR for the digital signal processing and demodulation, so clearly I need quite a bit of memory for all the other things that QDX is doing, and there's no way I can use 60,000 bytes for the frame buffer. So what I've done is I've reduced this to 800 by 300 pixels, and I send each of the scan lines on the display twice. So so you get 2 lines which are exactly the same sent. So to the monitor it looks like 800 by 600, but as far as the memory I'm using, it's 800 by 300, which is 30,000 bytes. I'm still very constrained on space, and particularly for the audio frequency sweep and RF sweep functions in the QDX, I need a large bunch of memory. So I actually share that with the frame buffer, and during the AF sweep and RF sweep, the screen is blank anyway, so that doesn't matter. So I can just disable the VGA during that period while the calculation is going on, and then re-enable it afterwards when the memory is no longer used. So I have to do that sharing. That's just a minor detail. So the only way that you can get this SPI peripheral to clock out 36 megahertz pixels is by using the DMA system on the STM32F401. DMA is direct memory access. And what this means is that you can set up this system to transfer blocks of memory from the RAM of the processor into a peripheral, or indeed to other place in the memory or whatever, entirely on its own without CPU involvement. So it uses very little CPU resources to do this. This is the reference manual for the STM32F401, and it goes to 847 pages, so there's quite a lot in here. I read and reread again all the sections on the DMA controller, because the DMA controller is key to being able to generate this VGA signal. And two of the key functionality here are the circular mode and the double buffer mode. The FIFO mode I'm using as well, but it may or may not be important. I'm not 100% sure about that. Obviously, I'm not the first to generate SVGA or from a STM32F401 or other STM32 processors. There's a number of examples on the internet, and I've put a link to those down below this video. But what many of them do is on the scan line here, they've got the horizontal synchronization pulse, and they have that generating an interrupt at the end of it, which sets up the base address for the DMA, and then they have another interrupt a certain period later. This delay here is called the front porch in VGA terminology, and is the delay between the synchronization pulse and when the actual display scan line starts for showing the pixels. Then you have on the other end, between the end of the scan line and the beginning of the sync pulse, what is called the rear porch. Now, in total, this scan line, the entire scan line, consumes 248 CPU cycles, or lasts for 248 CPU cycles at 72 megahertz. And during that time, we send 100 bytes here to output the 800 pixels. So what a lot of these other VGA generation examples do is they set an interrupt up on the timer at the end of this front porch, and in that interrupt they enable the DMA transfer. Now, the problem with this is that if there's any latency involved in servicing this interrupt, you get this horrible jitter on the display, and the whole display goes fuzzy and looks awful. So each line has a variable amount of left or right shaking. Each of these pixels is displayed for only 2 CPU cycles of the 72 megahertz clock. So you can see that you very easily end up in a situation, even if you only have 1 cycle of variable latency in servicing the interrupt, which starts the DMA, you very easily end up in a situation where you have this horrible jitter, which ruins the stability of the picture and makes it look awful. So one of these links called jitter in the matrix, or glitch in the matrix, which is linked below, goes into very great detail on how he resolved all of these problems by various interesting techniques. He was able to get a stable picture. I tried all of the things which he had on his page, and I could not get my picture to be stable. And the reason for this is that in QDX, DMA is already being used for the I2S transfer. So the I2S transfer is transferring data at 48,000 samples per second from the ADC peripheral into the microcontroller. That's being done to implement the SDR. So our DMA is already busy on the I2S transfer, and it's also doing other things as well for the serial port. Now the extra serial ports are involved. So we have several different DMA channels running, and what I believe happens is that at the time you start this DMA for the SPI transfer of the scan line, if the DMA and the bus matrix in the STM32 is already busy, it has to wait for that transaction to finish before it starts this one. So this was a very, very big problem that I had that seemed initially very difficult to resolve. Then one night, in the middle of the night, as sometimes happens, I had an idea to use the DMA in the circular buffer mode. And what the circular buffer means is that it will transfer one set of bytes from memory to the SPI peripheral, and then rather than then generate an interrupt and stop working, it will immediately start again from the beginning, and it will keep transferring that in a circular way on and on and on without interruption. And what this means is that there is no possibility at the time the DMA is being started of any variable cycle latency here in the beginning of the DMA due to variable latency in the interrupt servicing routine, or due to the DMA already being occupied with other things. Because it's running continuously, so nothing needs to start it, and it doesn't need to wait for any transaction to complete before it can continue. This in itself would not solve the problem, because once the DMA process is running, you can no longer change the base address here, so the start address of what is being transferred. But the STM32F401 has a very interesting feature in that it has this double buffering. So there are two different memory base addresses on alternate passes through the circular buffer. First it will use the base address 0, and then on the next line it will use base address 1. So what I did was I set up an interrupt here at the end of the DMA transfer, and this interrupt is the service routine is then used to check a bit which shows whether it's using buffer 0 address or buffer 1 address, and it sets up the base address of the non-used buffer, which can be written because it's not actually being used for the active transfer, to the following scan line. So if you remember that we've got multiple scan lines here going across of the monitor, if the DMA transfer is working on this scan line, for example, then at the completion interrupt of this DMA transfer, I set the following scan line to be this scan line while it's being sent. Actually, sorry, that's slightly incorrect. At the completion of this scan line, the DMA will automatically begin the following scan line, and I have to set up the address of the scan line after that here. So when it finishes this scan line and it starts this one, this address is already set up and it's ready, and at this interrupt I can then set up the scan line of the next one, and so on. So in this way, the interrupt handler is actually setting up the scan line after the one currently just started, and that scan line doesn't start until 2048 CPU cycles later. So if there's any jitter in this interrupt service routine or any other interruption or delays, you've got a whole 2048 CPU cycles to play around with before you end up with any problems. So it results in an absolutely rock-solid display. I was very proud of this idea because I haven't seen it anywhere else on any pages which I was able to find or mentioned anywhere. So I was very proud of coming up with this idea that completely solves the problem. It also means that the CPU in the QDX spends very little effort on doing the VGA generation, simply because all it has to do is on those DMA interrupts, which occur at a rate of 35,000 something times per second, it just has to set the base address of the alternate registers here for the double buffering to the following scan line. And that doesn't consume very much CPU activity. It's not a heavy job at all. It's just computing the next scan line and setting it in a register. Now, the only remaining detail to sort out is that the scan line is being now sent routinely and with no interruptions, no latencies, no jitters or anything. However, the synchronization pulse could be occurring anywhere in this scan line, and that is something that we need to take care of, because we need to synchronize this transfer to the synchronization pulse, the H synchronization pulse, such that the display is the scan line is properly centered on the VGA monitor. Now, this turns out to be very easy to do, and I only need to do it once, because after that the H-sync pulse is generated exactly every 2048 CPU cycles, which is exactly the time taken by the DMA. So all I need to do is, on this interrupt service routine for the end of the DMA transfer, circular DMA transfer, all I need to do is the first time that executes, and only the first time, I need to just set the timer value that generates the H-sync to a particular value that will account for the, so if this is the timer pulse and this is the what they call the front porch, and this is where the video starts, I just need to set at the right moment, at the end of the completion here, I need to set at the timer value such that this H-sync pulse will occur at the correct moment to synchronize the start. And I did that experimentally. You could probably think about it. So you could say, well, if this is the ending pulse, what should the timer value be at this moment? If it was 0 here, for example, if it was 0 here and the H-sync pulse is generated just afterwards, then what should the timer value be at this point by calculation of all the parameters according to the SVGA specification, and enter that. It just wasn't worth thinking about. It was very easy just to do it experimentally and find the right value. The only other thing I should mention is that if this is the monitor and it's scanning across, there are here 800 pixels. This is a 100 bytes at 8 pixels per byte, 8 bits per byte. And now that I'm running the DMA transfer continuously, effectively there's this period at the end of each scan line and at the beginning of each scan line, and the synchronization pulse is somewhere in this period, with the rear porch here and the front porch from the end of the pulse to the beginning of the display as it wraps round. And these this timing turns out to require an extra 28 bytes as you go across here. So, well, that would be an extra 224 pixels, or an extra 28 bytes. So now the DMA transfer, instead of transferring at 100 bytes to get 800 pixels, now it has to transfer 128 bytes. And what that would mean is that I have to increase the size of the frame buffer to 38,400 bytes, of which these 8,400, so all of this period at the end here of each, so when it's not showing pixels anymore, but it's just in the blank period, that I'm just buffering up the circular, padding out the circular buffer, giving it time to start the next scan line. These would all be zeros. So I'd be wasting 8,400 bytes of memory in zeros and increasing the size of my frame buffer to 38,400 bytes. It turns out experimentally that this is not necessary. I can let this DMA transfer just overrun into the next memory, whatever's in the next memory, which will be the next scan line until the end here of the frame, in which case it'll be who knows what, some other variables. And it doesn't matter. You can send all this junk to the VGA monitor, and in this period, this non-displayed period over here, these 28 bytes can be whatever you like. The VGA monitor just ignores them completely. They don't have to be zeros. So that meant I could keep at the 30,000 byte frame buffer and just ignore this thing going on at the side, whatever memory was being transferred at the side. Of course, then I had to write code to plot pixels on the screen, code to write characters on the screen, code to use all the escape codes to set the cursor position, and all the escape codes that are interpreted by a VT220 terminal, or a subset of them. I had to design a character set and a font rather, and of course, I googled to try and find a suitable font. It turns out you need a font 10 pixels wide and 12 pixels high, so that you can fit 80 by 24 characters onto an 800 by 300 pixel display. And of course I couldn't find any font that came anywhere near to that required resolution. So in the end, after several hours of wasted Googling, I just decided to get on and do it myself the old-fashioned way, typing in ones and zeros, and that worked quite well, and the result is quite nice there, as you see. As far as the practical modifications to the board go, as I mentioned before, I have this small cut-off piece of PCB which I put two 4-pin headers on, and I got some very thin wires going from there to the microcontroller chip, because it's necessary to solder those wires directly onto the chip. To make those wire connections, I took apart this old relay, which was in otherwise uselessly bad condition with very bent contacts there, and the coil is wound with very, very thin wire, so I was able to get some of that wire out and use that to make the very, very thin connections to the microcontroller pins with a very fine pointed soldering iron. So not very easy to do, but it was something that was not impossible. Later I have this fluff of wire. The kids thought that it would be fun to attack this relay coil as well. Wasn't me. And what I've done over on this side is to remove the transistors which drive the PTT ports and just bypass them, and so that the signal is sent direct to the 3.5 pin header. So you wouldn't be able to use the PTT port after doing that, but you'd be able to use this 3.5mm as a as a serial port. I actually left in the 470 ohm resistors, and one of them I took out and then lost it, and decided I would try with leaving it in to minimize the modifications. So this is the tacked on 470 ohm resistor. The 470 ohm resistors in there don't affect the working of the serial port, but they will give you some degree of protection for your sensitive microcontroller over here in the event that you short-circuited something. So here we are on the top side of the board, and you can see the video, the VGA cable was cut off and a 4-pin header connector installed, and here is the same thing to a PS2 keyboard. So I couldn't find any PS2 connectors suitable, so I just used those. And here at the other end I'm using a normal 3.5mm stereo jack to make the connection to the QLG2 USB to serial converter. On the USB to serial converter I have fitted the jumper here at the row of jumper positions here, such that it uses 38.4K baud mode, and I'm connecting the ground pin and the RX and TX pins. Actually the ground pin seems to have come off, I have to fix that, here on this 6-pin header on the side, and I've moved 2 of the jumpers so that the serial port, instead of being connected to the GPS module, is now connected to this 6-pin header, which I've connected to the QDX. Just one way of doing it. You could use any USB to serial converter. It would have been nice to be able to supply an additional serial port in software via the USB cable, but in QDX the USB basically has the equivalent of a USB hub, which is, so your USB cable comes in, and then the USB hub splits out to a COM port for serial, and it splits out to an audio port for the audio to and from the QDX. And in USB peripherals, there's these things called endpoints, which are the communication channels via USB to the USB host, the PC. And the USB peripheral on the STM32F401 has only these 4 endpoints. Now, endpoint 0 is always used for control of the USB peripheral, so that's not accessible to us. Endpoint 1 is used as an interrupt endpoint for the COM port, and endpoint 2 is used for data for the COM port. And that's just the way that the COM port standard operates, the virtual serial COM port operates. It uses 2 endpoints, one for interrupts and one for data. And then the third endpoint is used for the audio in, out. So if we were to implement a second serial port via USB, we would need to have more endpoints, which just don't exist on the STM32F401. It only has these 4 endpoints, and we would need 2 additional endpoints to be able to do another serial port here, because that's just the way the serial port works. So it would have been nice, but we can't do that, so I've opened the USART serial ports on the microcontroller chip. So the pins in use on the microcontroller are shown here. Very fine wires are required. If you wanted to use one of the serial ports, it's conveniently wired to the 5th of the pin headers on the top left corner of the board, and the other pin of the serial port is one of the corner pins of the STM32, which is much easier to solder to. So for that serial port, it would actually be a lot easier. One more detail is that this serial port 2 is only available on the revision 3, revision 3A PCBs of QDX, because in the original version 1 PCB of QDX there was a daughter board with the T60 which was actually powered by that pin. So the QDX knows that it's on a revision 3 PCB, and it makes sure that it only enables serial port 2 if you've enabled it in the configuration and if it's on a revision 3 or 3A board. So the serial port 2 is only available on the revision 3 3A board. Of course, serial port 3 using the 3.5mm jack is also only on the revision 3 3A board, because the 3.5mm connector was added in revision 3 and 3A. On the original revision 1 and the revision 2 boards there's no jack, so the serial port 3 would work. It would just require pins to be soldered to the microcontroller on those PCB revisions. So you don't have the advantage of that convenient port. One other nice little thing to show you, which I implemented just to show off the graphics. In computer terms, something known as an Easter egg means a hidden feature which can be accessed by some secret method in a piece of software. So what I've done here, I've implemented an Easter egg in QDX. If you press the M key while you're at the menu, what do you get? You get the Mandelbrot set. So a nice demonstration of fractals to demonstrate the 800 by 300 pixel resolution of this VGA output. Just a cool thing. So there you have it. I think it's quite a cool hack, and if you do decide to try this, then as I said, please do not blame me if you short something or break something. It does require very fine soldering, but it is quite cool. The serial port 3 conversion just by removing a couple of transistors is much easier to do and could be useful to many of you. So thanks for watching, and I hope you enjoyed this and learned something from it. It was a fascinating project for me. I learned a lot about the insides and operation of the STM32, the DMA peripheral, SPI peripheral, and all those timing constraints. Really fascinating stuff. Thank you. See you again soon. Bye bye.